In this video, we shall look at a couple of review problems on the topic of torque on current loop. First, a brief introduction on the subject. Let's assume first you have this circular loop, and this loop carries an electric current I. The surface area of this loop is, let's say, a meter squared. A loop carrying current in this manner has magnetic moment. The expression for this magnetic moment is the current I times the areal vector A. Or since the area vector A is just the area A times the normal vector n hat, where the normal vector n hat goes up like that. So this normal vector lies in the direction perpendicular to the plane of that area. So therefore, that is also the direction of the magnetic moment. A simpler way of determining the direction of this magnetic moment is by using the right-hand rule. Assume you grab this loop with your right-hand fingers, and your right-hand fingers curl in the direction of that electric current. The direction of your thumb represents the magnetic moment. So what that means is, if I have the direction of current in this way, if I pretend to grab this loop, then the direction of the current represented by that curl of my right-hand fingers is like that, and this is the direction of magnetic moment. So in this case, the magnetic moment is going downward like that. The areal vector is also going in that direction. Having introduced the magnetic moment, let's assume the same loop is placed in a magnetic field, B. So this magnetic field and the magnetic moment makes an angle, say alpha, with respect to each other. Then we say the torque exerted by this magnetic field on that loop carrying current I is just the cross product of the magnetic moment and the magnetic field. The magnitude of that torque is given by the magnitude of the magnetic moment times the magnitude of the magnetic field times sine the angle between them. And since mu, the magnetic moment, is just I times A, the magnitude of the torque is then I A B sine alpha. The unit for torque is just Newton meter, and unit for mu is ampere meter squared. Since this loop carrying current has a magnetic moment associated with it, we can write down an expression for the potential energy U of a magnetic moment in a magnetic field, and the expression is given simply as follows. It's minus the dot product of magnetic moment and the magnetic field, and of course the unit is joules since we are talking about potential energy. Let's look at the first problem. A circular loop of wire with area 9 cm squared, that is this loop, and this area is 9 cm squared. It carries a current of 17 ampere. The loop lies in xy plane. As viewed along the z-axis, looking toward the origin, the current is circulating counterclockwise. That means the direction of the current is like that. Because since the plane of the loop is the xy plane, so that's the xy plane, the z-axis is coming towards you, and you're looking down the z-axis towards the origin, and the current is circulating counterclockwise as represented there. The torque produced by an external magnetic field is given by that expression right there. For this orientation of the loop, the magnetic potential energy U is negative. The magnitude of the field is 2.8 Tesla. Find the magnetic moment of the current loop and also determine the components of the magnetic field, Bx, By, and Bz. So first, let's determine the magnetic moment. The magnitude of it is the electric current times the surface area of that circular loop. The electric current is given to be 17 ampere. The A is 9 cm squared, so 9 over 10,000 meters squared. And the answer is 0.0153 ampere meter squared. The direction of this magnetic moment using the right-hand rule that we talked about earlier is coming out of the board. So the direction of it is parallel to k hat. So we can write the magnetic moment in vector notation as follows: 0.0153 k hat ampere meter squared. Now let's do part B. Before we do part B, let's note an information that is given to us. Now we are told that the magnetic potential energy U is negative. Now since the magnetic potential energy is given as minus the dot product of the magnetic moment vector and the magnetic field vector, and since mu is in a direction of purely k hat, B could have all three components, but the fact that the energy is negative, that tells us that the Z component of the magnetic field has got to be a positive number. So the Z component of that magnetic field is like that, and this BZ is a positive number. Only then you will have the potential energy being negative because there's already a negative sign there. So let's note that on this corner. Torque is given by a cross product of two vectors. One is the magnetic moment, which we know here it has only the Z component. So the I component is 0, the J component is 0, and the K hat is 0.0153. That is the K hat component. The second row is occupied by the components of the magnetic field, Bx, By, and Bz. We are given the expression for torque. It's just that. So let's cross out the I in two mutually perpendicular directions to get the x component of the torque. That is this times this minus this times that. So that means the x component of that torque according to this expression is minus By times 0.0153. And that must be the same as minus 6 times that, 10 to the power minus 3. And you can solve for By. When you do that, you get By to be 0.392 Tesla. Now let's look at the J component. We cross that out in two mutually perpendicular directions. So the J component, or the Y component of the torque, is this times that minus this times that. But then there's always a minus sign in front of J hat. So that means the J component, or the Y component of the torque in this case, is Bx times 0.0153. And that must be the same as 8 times that. So 8 times 10 to the power minus 3. And you can solve for Bx, the x component of the magnetic field. And you get 0.523 Tesla. So we have the x component of the magnetic field now, 0.523 Tesla. That leaves us with only the Z component. What is it? Well, we can no longer find any additional information from this determinant. However, we are told that the magnitude of the magnetic field is 2.8 Tesla. So that means the magnitude squared is the same as Bz squared plus By squared plus Bx squared. So B squared is 2.8 squared. Bz we don't know. That's what we want to solve. By is 0.392 squared. That's from here. Bx squared is 0.523 squared because we know Bx from there. And solving for Bz, we get 2.723 Tesla. And that solves the problem. Problem 2. A coil with magnetic moment 1.4 ampere meters squared is oriented initially with its magnetic moment parallel to a uniform magnetic field with strength 0.85 Tesla. Find the change in magnetic potential energy of the coil when it is rotated 180 degrees so that its magnetic moment now is anti-parallel to the magnetic field. So let's look at the initial and the final configuration of that coil. So initially, that is the coil, the magnetic moment is like that, and the magnetic field is also like that. So they are parallel to each other. So in this case, the magnetic potential energy is given by minus B dot mu, or mu dot B. So that is just minus the magnitude of mu times the magnitude of B times the cosine of the angle between them. In this case is 0 degrees. So cosine 0 is 1. So you get just minus mu B. So minus mu is 1.4. That is the magnetic moment of this coil. The magnitude of that magnetic field is 0.85 Tesla. So 0.85 there. And that's going to give you a potential energy of minus 1.19 joules. So let's write it here, minus 1.19 joule. Now let's look at the final configuration. So you have the loop and it's been rotated 180 degrees. So the field is that way. The magnetic moment is that way. So they are anti-parallel to each other. So the final magnetic potential energy is given by minus mu dot B minus mu times B times cosine of the angle between them. In this case, now it's 180 degrees. Mu is 1.4. The value of B is 0.85. Cosine 180 is minus 1. And the answer is positive 1.1 joule. So there we have it. The final magnetic potential energy is given by 1.19 joules. Since we are interested in the change in the potential energy, so the change in potential energy is given by the final potential energy minus the initial potential energy. So 1.19 minus 1.19. And that's going to give you positive 2.38 joule for the answer. And that solves the problem. Thank you for watching.